Frame fabrication. The production process begins with the fabrication of the motor frame, which provides a sturdy structure to support all components. The frame is built to precise specifications to handle the 2,240 kilowatts power output and 3.3 kilovolts rating.
Stator core assembly. The stator core, responsible for generating the magnetic field, is assembled using high-quality laminations. This component is essential for efficient magnetic performance and minimizes energy losses. The stator undergoes VPI, where a vacuum removes air pockets and resin is infused to strengthen the coil insulation, protecting it from moisture and mechanical stresses.
Stator stacked into the frame. The impregnated stator is securely stacked within the motor frame, ready for the integration of the shaft and polar wheel.
Shaft and polar wheel machining. Precision machining of the shaft and polar wheel is performed to ensure optimal alignment and fit. The shaft is critical for torque transmission, while the polar wheel supports the magnetic poles.
Shaft stacking and pole assembly. The shaft is inserted into the polar wheel and the poles are carefully assembled. This part of the process is vital for accurate positioning to achieve balanced motor operation.
Final assembly and testing. The assembled motor undergoes customer-witnessed inspections and rigorous testing for quality and performance. Once verified, the motor was packed and dispatched from WEG India.
On-site installation and operation. Upon delivery, the motor is unpacked and the base frame is fixed. The motor is then assembled and tested at the site before entering full operation.
This thorough production process ensures that each SDA 1400 motor meets performance standards, providing reliable, high-efficiency synchronous motor functionality for industrial applications. Motor rewinding and remanufacturing are essential processes for restoring large AC and DC motors to peak operating condition, especially for high-capacity units like a 5,000 kilowatts wound rotor motor or a slow-speed vertical water pump motor. Disassembly is the initial step where each component, including the stator, rotor, and other internal elements, is carefully removed and inspected for wear or damage.
Technicians at facilities like Koffler in San Leandro, California, expertly rewind and service motors of all sizes and types. Their capabilities include both random winding for multi-strand stator coils and layer winding for rotating field coils. For example, the random winding process involves precisely placing multiple strands of wire into the stator, ensuring an even distribution of electrical load. This technique is critical for rotating exciter rotors, where each strand must be insulated to prevent electrical shorts.
Layer winding, used in reassembling large generator pole pieces, requires rectangular wires that fit together in a structured, layered pattern, maximizing efficiency and durability. Another crucial step is the replacement of lamination in large generators, such as a 3,500 kilowatts unit, which is essential for restoring magnetic performance. The DC armature rewinding process includes insulating coils and wedging, which firmly secures coils within the stator, adding to the motor's stability under heavy operation.
After rewinding, technicians connect and secure output coil termination blocks, ensuring all connections are intact. Rigorous testing verifies that output voltage across all three phases is consistent, confirming operational integrity before reassembly.
The Siemens SGT-800, a 50 MW class industrial gas turbine, is designed to deliver high efficiency and low emissions, making it ideal for a wide range of power generation needs. Developed in Sweden in the 1990s and initially introduced as a 43 megawatts turbine, the SGT-800 has evolved to over 50 megawatts through continuous improvement. This turbine is now used globally across multiple sectors, including power production, utilities, and the oil and gas industry.
The SGT-800 combines a robust design with flexibility in fuel and operation. It is engineered to maintain optimal performance across various applications and operating conditions, making it suitable for both baseload and backup power. A key aspect of the SGT-800's design is its two-bearing rotor configuration, which contributes to reliability and simplifies maintenance. The 15-stage compressor, equipped with variable guide vanes in the first 3 stages, enhances efficiency by adapting to different load requirements and optimizing performance at various ambient temperatures.
To accommodate hot climates, an option allows the modification of the compressor vanes from stages 3 to 15, increasing power output and efficiency in high-temperature conditions. The vertically split compressor casing further aids in maintenance efficiency by allowing on-site replacement of individual blades or vane segments.
The SGT-800 features a dual-fuel dry low-emission (DLE) combustion system, which enables clean combustion without the complexity of burner staging. This system supports a wide range of fuels, including those with high levels of inert gases, hydrogen, and heavy hydrocarbons. The combustor and burner designs are optimized for low emissions, achieving single-digit NOx and CO levels.
The turbine's 3-stage design is highly efficient, and its blades operate under challenging conditions. An effective cooling system and insulating thermal barrier coatings extend blade life and maintain optimal performance. Interlocking shrouds on the last turbine stage blades provide added durability, further enhancing the turbine's robustness.
The SGT-800 is available in 2 configurations, the Classic package and the Single Lift package. The Classic package includes the turbine and gearbox mounted on a single base frame with auxiliary systems positioned on a nearby skid. Alternatively, the gearbox can be directly mounted on the foundation to reduce transport weight. This package is compact, allowing for easy on-site installation and maintenance.
The Single Lift package offers a complete skid-mounted setup, including the turbine, gearbox, generator, and auxiliary systems, all with a minimal footprint. This design allows for quick installation and commissioning, reducing setup time to as little as 60 days. It also facilitates a fast core engine exchange, maximizing uptime and availability. Both package types can undergo operational testing before delivery to verify efficiency and output performance.
Siemens offers the SGT-800 as part of combined cycle and combined heat and power (CHP) plants. Its excellent steam generation capacity allows it to achieve high efficiency by utilizing exhaust heat for steam production, providing an effective means of converting fuel into useful energy.
With global organization, resource scarcity, and climate challenges, the SGT-800's proven reliability, low emissions, and high efficiency meet the growing demand for sustainable power solutions. Its adaptability and cost-effectiveness make it a prime choice for both industrial power generation and oil and gas applications worldwide. The power transformer manufacturing process begins with transformer design, where engineers determine specifications based on the application, such as voltage levels, capacity, and insulation requirements. Advanced software tools assist in optimizing the design for performance and reliability.
Once the design is finalized, the next step is the manufacture of windings and the transformer core. This includes selecting high-quality copper or aluminum for the windings, which are then insulated to prevent short circuits. The magnetic circuit is constructed using silicon steel sheets, carefully laminated to reduce energy losses due to eddy currents.
The wind-in assembly follows, where the insulated wire is wound around the core to form primary and secondary windings. This step is critical, as the precision of winding affects the transformer's efficiency and capacity. After winding, the transformer core and windings are combined to form the active parts of the transformer. This assembly must be done in a controlled environment to minimize contamination and defects.
Once the active components are assembled, the installation of grounds is performed. Proper grounding is essential for safety and functionality, ensuring that any fault currents are safely directed away from the transformer.
The next phase involves IA instruments for examinations, where non-destructive testing methods like insulation resistance testing and transformer turns ratio testing are employed. These examinations verify that all components meet safety and operational standards before proceeding further.
After thorough testing, the transformer enters the completion stage. This involves encasing the core and windings in a robust housing, typically made of steel, to protect them from environmental factors and mechanical stress.
Finally, the expedition stage prepares the transformer for shipment. Proper handling and packaging ensure that the transformer reaches its destination without damage. The last step involves assembly on the distribution box, where transformers are integrated into the electrical grid, ready to manage voltage transformations for efficient power distribution. Voltage transformation and regulation.
One of the primary functions of substations is voltage transformation, where electricity generated at high voltages in power plants, often ranging from 11 kilovolts to 25 kilovolts, is stepped up to much higher transmission voltages, typically between 110 kilovolts and 765 kilovolts. This increase minimizes energy losses over long distances by reducing the current in the transmission lines, in line with Ohm's law, where power loss due to resistance is proportional to the square of the current.
At distribution substations, voltage is again stepped down to levels suitable for commercial and residential use, typically between 4 kilovolts and 33 kilovolts. Finally, at local substations, voltage is reduced further often to 240/120ths of a volt in the US or 400/230ths of a volt in many European and Asian countries to meet specific consumer demands.
Power system protection.
Substations are equipped with critical protective devices such as circuit breakers, fuses, and relays to guard the grid against faults and overloads. Circuit breakers, for instance, can interrupt power flow in fractions of a second to isolate damaged sections and prevent cascading failures, a phenomenon that can lead to wide-scale blackouts. This functionality is essential. According to U.S. Department of Energy statistics, power outages cost American businesses an estimated $150 billion annually. Modern substations utilize advanced digital relays that offer rapid fault detection, enhancing system resilience and minimizing downtime.
Switching and control.
Substations facilitate switching operations that allow operators to isolate sections of the grid for maintenance, reroute power during emergencies, and regulate load flow. This is especially important in regions with varying demand levels, where load balancing is crucial to prevent stress on specific parts of the grid. High-voltage substations frequently include bus bars, conductive metal strips, or bars that serve as distribution hubs for electricity within the substation. These bus bars provide flexibility, allowing electricity to flow through alternate paths when primary transmission lines are under maintenance or repair. Integration of renewable energy sources.
As the energy industry transitions towards sustainable sources, substations are increasingly vital in integrating renewables into the grid. Solar and wind energy, both highly variable by nature, require sophisticated control mechanisms within substations to manage their fluctuations.
Load management and demand response.
To accommodate peak demand, substations support load management by redistributing power or adjusting loads in real time, often with the help of intelligent grid systems. In many regions, peak demand can be more than twice the average load, stressing power infrastructure if not managed effectively. Substations equipped with demand response systems can shed non-essential loads during peak times, which reduces the need for costly standby power plants and minimizes strain on the grid.
Ensuring power quality.
Substations are essential in maintaining power quality standards, including voltage stability and frequency regulation. Power quality is crucial because deviations can harm sensitive industrial equipment, disrupt data centers, and cause fluctuations in residential areas. According to IEEE standards, voltage variations in power quality should generally not exceed plus or minus 5% of nominal voltage, and substations use devices like voltage regulators, capacitors, and reactors to maintain these levels.
Digital and automated substations.
The integration of digital technology has revolutionized substation operation, allowing for enhanced monitoring, predictive maintenance, and real-time data analytics. Automated substations utilize intelligent electronic devices, IEDs, and remote control systems, enabling operators to manage substations from a centralized location. According to a report by Global Market Insights, the market for digital substations is expected to grow at a rate of over 6% annually, driven by increased demand for grid automation and the integration of renewable energy sources.
By using digital substations, utilities can achieve higher reliability and efficiency. For example, sensors in digital substations can monitor equipment conditions like transformer temperature and oil levels, predicting failures before they occur. This predictive approach reduces maintenance costs and prevents unexpected outages, improving overall system reliability. This section shows production of the two largest synchronous compensators ever produced in Brazil. Manufactured by WEG at its facility in Jaraguá do Sul, these massive machines mark a significant milestone in Brazilian engineering. Each compensator weighs an impressive 310 tons, stands 7 meters tall, and spans 11 meters in length, showcasing the complexity and scale of this innovative project.
According to Sinesio Tenfen, managing director of WEG Energia, the manufacturing timeline was remarkable, completed in under 10 months, a record for equipment of this size. These synchronous compensators are designed for critical roles in large-scale electrical power generation and transmission, with specific placement at the Marmeleiro 525 kV substation in Santa Vitória do Palmar, Rio Grande do Sul. This substation will connect power generated from wind energy sources, helping stabilize the electrical grid by compensating for reactive power and enhancing overall system reliability.
Transporting these massive machines requires intricate logistics. The first compensator will leave WEG's Parquet Drill 2, traveling by road via BR 280 to the port of São Francisco do Sul. From there, the journey continues by sea on a specialized 64-meter barge in the port of Rio Grande in Rio Grande do Sul before reaching its final destination. The transportation process underscores the immense planning needed for handling such enormous and delicate machinery. Building a large electrical generator at Siemens Energy's Competence Center in Mulheim involves an intricate production process that begins with the creation of the stator, the stationary part responsible for inducing voltage. First, the conductors are precisely inserted into winding stands and securely soldered. Each soldering point undergoes immediate ultrasound testing for quality assurance. The next step involves forming the stator core by stacking over 100,000 laminated steel sheets. These sheets are carefully aligned, clamped, and welded to create a robust core structure.
The rotor, or the generator's rotating component, is then prepared. Its production includes precision machining, where it receives a final mechanical finish for optimal performance. Once completed, the rotor undergoes dimensional accuracy checks for diameters and lengths, ensuring a precise fit within the stator.
A critical assembly stage, known as marriage, involves positioning the rotor within the stator core, which requires meticulous alignment. After this step, the generator moves to the resin impregnation stage. Here, all air pockets in the winding are vacuum sealed and filled with resin to enhance durability and insulation quality. The entire assembly is further inspected to ensure mechanical integrity and consistency.
Siemens Energy employs advanced testing methods before delivering the generator. The assembled generator is placed in a test field monitored by a control center where operational simulations verify performance and durability. The facility's state-of-the-art testing capabilities can also detect potential malfunction.
Once testing is complete, the generator is ready for global transport, facilitated by Mulheim's unique logistics setup with a direct river connection. This production process not only guarantees a reliable energy solution, but also aligns with Siemens Energy's commitment to sustainable energy production, supporting the transition to renewable energy sources. RSO inspection.
RSO, recurrent surge oscillation inspection, is one of the initial diagnostic steps in rotor rewinding. This technique detects shorted turns in the rotor windings, which can significantly impact generator performance and longevity. By using recurrent surge oscillations, technicians can identify electrical discrepancies without fully disassembling the rotor.
Removal and refitting of rotor copper bars.
The rotor copper bars are a key component in generating the magnetic fields necessary for power production. In this stage, technicians carefully remove the old copper bars for inspection and potential replacement. Any defects in the bars can affect the electromagnetic performance of the generator. New or reconditioned copper bars are then precisely refitted into the rotor, ensuring they align correctly with the rotor slots and maintain the generator's power output and efficiency.
Material identification for manufacturing the new retaining ring.
For manufacturing a replacement retaining ring, material identification plays a vital role. This involves verifying the material composition, typically using spectrometers or X-ray fluorescence techniques, to ensure that the replacement matches the original ring's metallurgical properties. High-quality materials resistant to high-speed centrifugal forces and thermal expansion are chosen for the retaining ring to enhance the durability and safety of the rotor assembly.
Rotor forging and shrink fit.
Once the replacement retaining ring is ready, the rotor forging process begins. Rotor forgings are specially manufactured to meet high-strength requirements. The replacement retaining ring is typically shrink-fitted, a process where the ring is heated to expand and then carefully placed over the rotors. As it cools, it contracts to form a tight, secure fit, ensuring that the rotor components remain stable at high speeds. This shrink-fit process is precise and requires skill to prevent mechanical stresses from misalignment.
Measurements and dimensional checks.
Measurements are repeatedly performed throughout the rotor rewinding process to ensure accuracy in assembly. Precision measuring tools and techniques are used to verify that each component, including the retaining ring, fits perfectly. Dimensional checks are particularly important after the shrink-fit process, as any misalignment can lead to operational inefficiencies or potential failure during high-speed operation.
Retaining ring measurement and replacement.
Retaining rings, which hold the rotor's windings in place, are critical for mechanical stability at high speeds. During this process, the retaining rings are carefully measured to assess their dimensions, wear, and integrity. Retaining rings endure considerable stress due to centrifugal forces, making it essential to ensure they are in perfect condition. If wear or defects are detected, the existing retaining ring is replaced with a new one. The process begins with the disassembly of the motor. Once opened, technicians carefully remove the old windings from the stator to make way for new, precisely measured copper windings. This replacement is vital as the windings are the heart of the motor's electrical functionality, dictating efficiency and performance.
Next, the rotor is prepared for banding. Banding involves tightly wrapping the rotor with a specialized material that reinforces its structural integrity, especially under high-speed operation. This banding material is designed to withstand both the centrifugal forces generated by the rotor's movement and the intense environmental conditions in which the motor operates. Proper banding is crucial for preventing any loosening or deformation during motor operation, which could cause failure.
Following banding, the rotor undergoes balancing to ensure smooth operation. Technicians perform an initial balancing to identify any irregularities in weight distribution. Any imbalances are corrected by strategically adding or removing small weights, thus achieving perfect rotational symmetry. After this, a final balancing is conducted to confirm that the rotor can spin evenly and without vibration, an essential factor for maintaining the motor's long-term health and performance.
Meanwhile, the stator is given an anti-corona treatment to enhance insulation. The stator windings are coated with blue epoxy anti-corona paint, which helps to resist the degradation effects of high-voltage electrical stresses. After painting, the stator undergoes vacuum pressure impregnation, VPI, a process that drives epoxy deep into the windings, ensuring full insulation and protection against moisture and contaminants. Once the impregnation is complete, any excess epoxy is carefully removed, leaving a smooth and clean surface.
With all components prepared, the motor is reassembled with precision. The stationary runner, a key part of the motor's assembly, is carefully installed to guarantee proper alignment and stability. Following assembly, the motor undergoes rigorous testing to confirm its performance. It is mounted on a custom-built stand designed specifically for this motor's testing, ensuring stability and accurate test results.
During testing, the motor's electrical, thermal, and mechanical performance parameters are meticulously documented. Any abnormalities are addressed, and adjustments are made if necessary. Once the motor passes all tests and meets specified performance criteria, it is certified for shipment. This thorough certification ensures that the motor will reliably power the pump at the submarine dry dock, maintaining critical operations at Pearl Harbor.
The GH30 line hydrogenerators exemplify innovation in hydroelectric technology tailored for mini hydro and small hydropower plants. These generators are versatile, designed for use with different turbine types, including Francis, Kaplan, and Pelton turbines, each suited to different hydraulic conditions. With a capacity range from 950 to 3,000 kVA and a variable number of poles, 10 to 24, GH30 hydrogenerators are engineered for high flexibility and efficiency.
The construction of GH30 hydrogenerators integrates several key features that enhance their durability and performance. The frame, built from carbon steel sheets, is robust, ensuring structural integrity and accommodating necessary ventilation and accessory fixtures. The cylindrical, rib-free shaft design aligns with IEC standards and is crafted to withstand fatigue, stress, and deformation. In some cases, an inertia flywheel is integrated directly into the shaft, optimizing space and reducing maintenance requirements.
GH30 hydrogenerators are also equipped with advanced monitoring and protection systems, including thermal sensors, voltage and current measurement devices, and speed sensors. These features allow for real-time tracking and control of generator operations, promoting reliability and extending service life. Through optimized weight-to-output ratios, tailored electromagnetic configurations, and reduced maintenance demands, the GH30 line offers a sustainable, efficient solution for small to mid-scale hydropower applications. Manufacturing the coils.
The process begins with selecting high-quality copper wire, which is then wound into coils according to the motor's specifications. Each coil is carefully wound to precise dimensions to ensure optimal electromagnetic performance. Once the coils are formed, they are insulated with materials like polyester or fiberglass to enhance durability and electrical insulation.
Rewinding the coils.
Rewinding is often done when an electric motor needs repair or maintenance. The damaged or worn-out coils are first removed, and the core is cleaned. New copper wire is then wound around the motor's core in the exact specifications required for the motor to ensure efficiency. This rewinding process restores the motor's power output and extends its lifespan.
Electrical testing.
After rewinding, the coil undergo rigorous electrical testing, including resistance and insulation checks, to verify the integrity of the coils and ensure they meet safety standards.
Vacuum pressure impregnation, VPI, with resin.
The final step is impregnation, where the coils are treated in a vacuum chamber with resin. The vacuum pressure impregnation, VPI process ensures that the resin penetrates deeply, enhancing coil insulation and resistance to moisture, heat, and mechanical stress. This thorough process results in coils that are durable, efficient, and ready for reliable operation in the motor. Manufacturing generators, steam turbines, electric motors, and gearboxes specifically for the sugar and ethanol industry plays a critical role in enhancing efficiency and sustainability across each stage of production. This sector requires highly durable and reliable equipment to handle the intense demands of processing and production.
Generators and steam turbines power the facilities, delivering stable and efficient energy crucial for around-the-clock operations. These systems are designed to provide consistent power under varying loads, ensuring that all machinery operates seamlessly. Electric motors and gearboxes support critical functions across the production chain, including the operation of cranes, feed tables, crushers, chippers, and levelers. This equipment enables the smooth handling and processing of sugarcane and other biomass, reducing downtime and maximizing throughput.